Thank you, Marka, and I would like to extend thanks to all the organizers of this wonderful workshop. It's a real pleasure to be here. My talk is going to be based on some work, part of it is already published, part of it we're going to publish in the next couple of weeks, and it's based on the work with all these great collaborators whom you can see here. Especially maybe I should mention Mike Toomey and Anton Chudaikin, who are on the job market this year, so please hire them, they are terrific. Okay, so the plan for my talk will be as follows. First, I'm going to overview the recent DESI results on the detection of dynamical dark energy. Then I will explain like what features in the data are driving this tension, driving this evidence for dynamical dark energy. Then I will talk a little bit about the phenomenological implications and interpretations of this data. And then I will argue that to make progress with these interpretations, we need to bring in more data. And one example of such data that seems to make a difference in this particular setup is the full shape of the clustering information from the power spectrum and the bispectrum. And then I will introduce some of the new tools that boost the information from this method, which is the simulation-based priors and a little bit, the long-loop bispectrum. And finally, I will present the results from the independent reanalysis of the public DESI DR1 full shape data. All right. So first, some overview and motivation. So I should say thank you to Sadia, who already presented the DESI results, so I don't have to say much. Basically, the DESI collaboration has reported some evidence for dynamical dark energy parameterized by these parameters W0 and WA. W0 is the value of the equation of state of dark energy now, and WA is the derivative with respect to redshift, at redshift 0. And then the cosmological constant value is W0 minus 1, WA is 0, so that will be here. So DESI reported some 3 sigma evidence for W0 WA in a combination of the BEO and the CMB data from Planck. And then you can add also some supernova data, and in general, then this evidence for dark energy becomes slightly more significant, so all the way up to 4 sigma. And obviously, this is a very serious claim. It's a very serious, evidence for new physics, and even New York Times wrote about this. So you can see that everything is very serious. So we also need to scrutinize these results very seriously. And before moving forward, let me just say that the results of DESI are based on the analysis of galaxy clustering at various redshifts. So there are various tracers involved. And these tracers, they have different names. They're shown here. Bright galaxy samples, bright galaxy sample, BGS, red luminous galaxies, LRG, emission-like galaxies, LG, and quasars, QSO. So I'm going to be using these abbreviations. I apologize to particle physicists for that, but okay, at least here I just mentioned that there are all these different types of galaxies, tracers. Okay, I'll be using these abbreviations. The only thing you need to know, this correspond to different galaxies. All right, so let's first talk about the kind of point of this W0 WA. So what's driving this evidence? As Satya explained really well in her talk, DESI is measuring distances across redshift, and there are various ways to present this information. One way is to compute the so-called diameter of the volume average distance, which is kind of a geometric mean of the angular diameter distance and the radial distance to the galaxies. And then another parameter would be the ratio of the radial and the angular distances, called the Alka-Paczynski parameter. And here you can see some DESI data points with some theoretical curves. So let me explain what is going on. So there are two key effects that are driving the evidence for W and WA. So the first thing is that these distances, normalize to some fiducial value. You can see that the DESI measurements are offset with respect to the prediction or extrapolation of the CMB-based Planck best fit model. So there is this overall offset, a little bit of the offset here. So the first thing that drives the tension is this offset. Okay, so this offset you can think of as a tension in the inferred value of omega matter in the CMB and large K structure. And in principle, you can reduce this offset by, let's say, fitting lambda CDM omega matter from the combined data set of CMB and DESI. And in that case, you're going to get this gray curve. Okay, so you can see you can eliminate this offset, but still there is a little bit of tension in the data, and in particular, you can see that there are few data points that lie kind of a little bit below the baseline after you fix the baseline, and also here in the FAP plane, you can see there are a couple of data points lying just below and a couple of data points lying just above the baseline. So what dynamical dark energy allows you is to really like dive into these data points here. So dive here and then jump back. So it really allows you to go like this. And something similar is happening also in the DV plane. Also, with phantom dark energy, you can kind of go through all these data points, dive in and jump back and go through these other data points. And it's very important for this to feed the data for dark energy to really have this behavior. So first, in order to dive, you need to start accelerating with acceleration. So to accelerate, the universe needs to expand in the so-called superinflationary regime, where the third derivative of the growth factor is positive. So first, you need to accelerate faster, and this is what allows you to like dive here, and then it should start breaking very, very suddenly. This is what you need in order to hit these other data points at lower redshifts. And this feature, the phantom behavior. Okay, so in order to accelerate kind of with acceleration in this superinflationary regime, your effective equation of state needs to cross the phantom divide. So W needs to be less than -1 at some redshift. And this is a very robust thing that the data suggests. And it doesn't depend on a particular parameterization. There are different parameterizations on the market. And all of them basically are telling you that around redshift 1, so that is around here, data really wants dark energy to be phantom. And another way to think about this is that if you start to kind of addressing the signal, building some models and trying to fit the data, you will see that if you're just using the simple kind of quintessence type of models with a single scalar field, it's not going to work in the sense that it can kind of account for the first effect, which is like the tension in omega matter, but it doesn't have the phantom behavior, so it will never be able to provide as good fit to the data as the data wants. And in particular, the kind of scalar field potentials with the Hilltop potential, exponential potential, they basically provide a fit which is only slightly better than the cosmological constant. So within 2 sigma is consistent with the cosmological constant. So really, to get a good fit, you need to cross the phantom divide. And obviously, if we're talking about single fields, this seems like a crazy thing to do, because this will require the violation of the null-engine condition. But however, the important point to make here is that this parameterization that DESI uses is an effective parameterization, and in principle, you can effectively go phantom without actual violation of the null-engine condition if you allow for interactions of dark energy with something else. For instance, there was a nice paper by Justin Curry and collaborators on the dark UCD model, where you have dark energy axion, which is kind of dark UCD axion that interacts with dark matter, some fermion, and then the dark matter has mass changing with redshift. And first, you can kind of dump energy from dark matter into dark energy and make it accelerate faster, and then you can dump the energy back into dark matter and make the universe, break. And basically, this way, you can really reproduce effectively this behavior of the equation of state, and it crosses the phantom divide without actual violation of null-energy condition. And this is a very general feature of dark energy interactive models. So for instance, Mike Toomey, a postdoc in my group, he has this model of that he calls K-mix, where you have a dark energy axion interacting with some moduli field, light moduli field, and this field doesn't have to be dark matter, just some extra scalar field, and this scalar field can again reproduce the same phenomenology of just moving the energy back and forth. You can totally go phantom and then go back, in the null energy respecting regime. So you see, obviously, it's relatively easy to kind of address the WNWA measurements by DESI, in terms of phenomenology. And the question is, okay, whether we can really distinguish these different models, different scenarios. Okay, there is some degeneracy, obviously. So we need more data to really test the predictions. And I should also say that the interpretation of the DESI results of WNWA also is not the only way to interpret the data. So this first part of the WA story that there is a tension in terms of omega matter. So this is something that you can try to address by solutions that don't involve anything having to do with dark energy. So for instance, this could be just a tension in terms of the tau, which is the optical depth of the universe at ionization. So there was a nice paper by Noah here that basically if you just shift tau away from the Planck best fit value, then you can totally account for the DESI's dark energy results without actual dark energy evolution. And same way, Steven showed that you can achieve similarly a good fit to DESI plus CMB data by allowing some small negative spatial curvature that is consistent with inflationary models. So altogether, I guess all these different scenarios that tell you that the fate of WNWA is unclear at the moment, and we really need more information to kind of say more precise statements about this. So in my talk, I'm going to argue that this extra information might come from the full shape of the galaxy clustering. Okay, so what is this EFT-based full shape analysis? The idea behind this is to analyze the large-scale structure data same way as we analyze the cosmic microwave background data. As we know, we can measure the CMB anisotropies really well. Well, for instance, with Planck or some other experiments, SPT or ACT. And then the CMB anisotropies, like the temperature anisotropies, they represent a Gaussian random field. We can compute its power spectrum. It has a complicated function in momentum space. And then, oops, I try to play the video. Okay. And you can see that this CMB power spectrum has a very strong response to a variation of cosmological parameters. And it's kind of remarkable that it can be fed with only 6 parameters. And you can see, for instance, how that the response pretty drastically to the change of omega matter. And this is how we get some of the strongest quantitative evidence for dark matter. Okay, so in terms of large-scale structure, the game that we want to play is pretty similar. So we observe galaxies, which are some density fluctuations on the sky, and we can measure their correlation functions. Now, in terms of the galaxies, we get access to the 3-dimensional information, so we can measure the power spectrum now, not on the sky, but let's say in 3-dimensional space. So we can introduce usual wave numbers, and we can compute a 2-point function, 3-point function, etc. So galaxy field is nonlinear. It has non-zero higher order correlations. And again, the shape of these correlations, is in principle some complicated function of cosmological parameters that has some significant response. So for instance, here I'm going to play the exact same game. I'm varying the galaxy power spectrum shape as a function of the dark matter abundance. And then you can see that, again, the response is pretty strong. Actually, it's stronger in relative terms than the response of the CMB. So in this sense, at least for this parameter, it seems that large-scale structure can provide an extra information. And actually, in the context of dark energy, as I said before, part of the DESI claims, they're driven by the fact that omega matter is different. And here we can measure omega matter from the shape. So this tells you what is the kind of the main channel that we're going to use to improve over DESI. All right. Are there any questions at this point? Okay. Good. So if not, yeah, let me proceed. So obviously, the problem with galaxies is that they're hard to analyze. They're a mess. They're very nonlinear. And this nonlinearity will be obvious if you just try to fit the galaxy power spectrum of linear theory. You will see that your fit will be good only on large scales, and then it will kind of it will start failing. But it fails not in a terrible way. It fails a little bit, so which kind of suggests that you can use perturbation theory to account for that. And this is exactly what we're going to do. And this failure of linear theory, this was obvious even back in the day with the first analysis of the SDSS data. So it was clear that the theory systematics was much bigger than the statistical errors of the data. So for instance, in this old paper by Max Tegmark, you can see that like the analog of the same picture that I just showed you, that linear theory kind of fails beyond certain scale. And then back in the day, people were using some phenomenological prescriptions, like adding the chi-squared terms, like similar to the Cantor terms, etc. But I mean, it was clear that there was no kind of robust systematic way to proceed. And this was one of the reasons why eventually kind of the field moved onto the baryon acoustic oscillations, which is a more robust probe that is immune to the nonlinear effects. But if we want to like really bring in new information, and also maybe to test some new models that are impossible to test with the BIO. It's beneficial to take advantage of the shape and try to predict it. And in general, there are two ways to do that. One way is to use numerical simulations, which is obviously a great idea for matter clustering, because for matter clustering, we have the full UV model, first principle, which is an n-body dynamics. And this model is valid on an unlimited range of scales. So if we could measure dark matter halos, I would just stop here and say, look, this is the method we need to use, and then go on, right? Because obviously we can predict dark matter halos very accurately. But however, the problem is the galaxy formation, that for which we don't have the first principle model. And another problem is that still, even though there was so much progress in simulations, and also there was a big assist for machine learning, still the simulations are a little time consuming, so we cannot explore the parameter space as effectively as we might hope to. And then an alternative is to use perturbation theory, or EFT, which is applicable only on a limited range of scales, but then on the scales where it applies, it gives you a very high accuracy and precision, and in principle, it's also good for exploring beyond standard model of physics, because you can recompute your theory model analytically relatively quickly. All right, so in terms of perturbation theory, basically the idea is that we are using Taylor series everywhere, okay? So for any function we don't know, we're just writing down Taylor expansion. For instance, we know that galaxies, here in this output of the simulation, galaxies correlate with dark matter field, which is represented by the gray structure. So there is some function that relates the observed galaxy field to the underlying matter field. And in perturbation theory, we just say, let's write down a Taylor series and parameterize coefficients in this Taylor series as three parameters that we call nuisance parameters, bias parameters, EFT parameters. It's all the same. This expansion will involve lots of operators, but if you go to large scales, you only need a finite number of them, and if you have finite precision, also that means that you need to keep track only the finite number of terms, and there are lots of terms that are not allowed by various symmetries, so in the end you're going to get an expansion which is relatively constraining. And basically this pretty much summarizes the EFT program, where we compute different correlation functions using perturbation theory and statistical averaging, which produces Feynman diagrams. And when you put all this machinery together, then you can really fit the shape of the galaxy power spectrum on quasi-linear scales quite well. And we've been playing this game in the last 5 years or so many times, and there were many brilliant codes that people wrote that do these calculations. So in the end, we can fit the data, we can extract some cosmological parameters, we can get some measurements which are competitive with CMB. So it was a lot of fun and very nice. Well, I was happy to see that the DESI collaboration adopted EFT full shape analysis as the main way to analyze the data beyond the BEO, which was very nice. But DESI, with their analysis, they only analyzed a limited part of the data, only the monopole and the quadrupole of all these different samples, and they didn't analyze the bias spectrum, for instance. Okay, so there was some room for us to improve. And in the previous iterations of this workshop, then I would go on and discuss different BSM applications, because obviously, the coolest part is to then try to extract some new physics models and, constraints on different extensions of lambda CDM that address the Hubble tension, that produce some complicated dark matter sectors or modify initial conditions during inflation. In my talk, I'm going to skip all these discussions. You can check out the previous editions of this workshop for these different applications. So now let me say a few words about the new tools that we're using to enhance the signal from the full shape analysis of the galaxy clustering. Yes, absolutely, yeah. Yeah. That's right, yeah. So at the moment, what we're doing, which might not be very effective, like for every single model would compute its prediction, and the predictions would be different, right? And then we just fit the data and see which theory fits the data better. And oh no, we're computing the shapes. So okay, something here is that, okay, so you see there are coefficients that we don't know, and we typically just marginalize over them with some conservative priors. But then the fields themselves, the shapes that the operators that appear here are fixed, right? And in principle, in some BSM models, that there will be additional shapes, right? So this is, for instance, something that well, Ennio and others are working on. So this is one way to do it. So in other models, what happens is that these operators are the same, but what changes is the growth function, right? For instance, for dark energy equation of state, like the growth function that appears in front of this overdensity fields will be different, right? That gives you another way to test these things. Yeah, yeah, sorry. They are scale dependent but redshift dependent. In principle, for every redshift, they will be like, they will take different values. And for different, yeah, they're scale independent. Yeah, absolutely. Yeah. Again, all scale dependence is captured by all these different operators in this expansion. Mm. Yeah. Right. Yeah. Yeah. The strongest effect, obviously, you'll get if you break the symmetries. Yeah, like the equivalence principle. But other things will also produce effects. Okay. I think there was another question. Maybe Mustafa. Yes. Yeah, eventually. Okay, so this is really a great question. I mean, obviously, for like cold dark matter, we can do fluid. There is no question. Okay, now there are cases like, for instance, neutrinos, massive neutrinos, that kind of we know that neutrinos are not a good fluid. But then what happens here is that there will be additional scales in this problem, additional small parameters that will allow you to write down an effective fluid description. So there was a nice paper, Senatore Zariaga, on the treatment of massive neutrinos. So effectively, you'll be able to write down fluid equations even in the presence of neutrinos. So it's like conceptually it's slightly more difficult. So when you have a scale like neutrinos, they have a big free streaming scale, right? But it's possible to identify small parameters and still write down effective fluid equations in that case. Okay. All right. Yeah, that's right. That's right. Yeah, eventually what we're going to do bispectrum, gamma power spectrum by spectrum, they will break these degeneracies, right? Okay. All right, any more questions? Okay. If not, okay, let me start talking about these new tools. Okay, so I mentioned this EFT, that seems to be very nice, but EFT is, again, fundamentally limited because it's just a Taylor expansion, and we know that Taylor expansions, they don't converge beyond the radius of convergence. When you hit the radius of convergence, it doesn't matter how many loops you keep, your prediction is going to be disaster. So in our universe, basically this happens when the linear density field becomes over 1, which roughly corresponds to the scale of 1 h over megaparsec. And a way to kind of visualize this is to take a look at the toy model of structure formation, a spherical collapse, where you can obtain a full kind of analytic exact solution, and then you can see that it features this pole. So basically what EFT does is that it Taylor expands this in terms of delta linear, but you can see when delta linear becomes greater than this number, which actually is not 1, well, it's around 2 or something, slightly bigger. But you can see that after that, obviously, it doesn't matter how many terms in Taylor series you will keep, it's not gonna, your delta nonlinear prediction is not going to improve, right? So obviously, when you go to small scales, you cannot use EFT, it's a complete disaster. Okay, so let's now talk a little bit about simulations. So our best kind of shot at the full principle way to simulate structure formation is to use the hydrodynamical simulation, where really we write down all differential equations for dark matter and gas particles and magnetic fields and everything that you can think of, and you end up with a lot of equations. You cannot solve them at once, so typically you truncate this system of equations in some way, and the way you truncate it is called a subgrid model. And obviously there are different ways to truncate it, different codes, they use different subgrid models. And even in this case, I mean, you can let it run and you can generate these wonderful pictures, but still the simulations are quite expensive. So what we're using is a cheap alternative to that is called the, well, in general, it's called the empirical models, and the one that, one of the models that is used very, very widely is the Hall occupation distribution model, which is basically the idea is that maybe we don't need to like simulate everything. So we know from observations and also from hydrosims that galaxies live in dark matter halos. So maybe we could just run an on-body simulation, get all the halos, and like paint the galaxies on top of this, right? Because we can generate a picture similar to that, kind of in a synthetic way without having to track all the galaxies, all the baryonic particles. So basically, we take a look at this dark matter distribution. We identify halos, which are fully non-perturbative objects, and then we assign some probability for this halo to have a galaxy. And then, we can think about halo having a central galaxy and also like smaller satellite galaxies, like the Magellan clouds. And typically, in the simplest scenario, you can think that the only parameter that matters is the halo mass. And in that case, the for the red luminous galaxies, for instance, the typical form of this distribution that is called HOD distribution for the centrals will be like a step function, like a Heaviside function. So basically, below certain mass, the halo is too weak to have a galaxy. After certain mass, it will have certainly a central galaxy. And then the bigger the halo is, the more satellites it might have. So you can write down like different parameterizations of these functions, and you can check, you can compare these HOD functions against the simulations, and indeed you can see that something that looks like a Heaviside step function, and then there is some sort of power law for the satellites. So this all makes sense, and this allows you to kind of easily produce the results of hydrosims. Now, this is the core of the simulation-based program, which is basically the idea to feed the data directly with the output of simulations. And I think that Urs is going to mention this in his talk. Now, the thing with the simulation-based inference program is that still, even if you use HOD, there is still a significant computational cost. And then the community kind of split into two ways, pursuing different ways to optimize this problem. One way is to run a small grid of high volume, high resolution, nice simulations, which is represented by the Abacus Summit. The only it's it's a great suite of simulations, but the problem is that the grid is too coarse for like precision statements about cosmology, so we cannot still kind of do full SBI. Another alternative route is to generate a large grid of small volume, low resolution simulations. So this was adopted in the Quixote suite, which works really nice on small volumes, but the problem is that we cannot analyze volumes greater than, let's say, 1 gigaparsec. And DESI eventually is going to have volume which is about 30 gigaparsec over h cubed, so it's much bigger than Quixote. So these different approaches, they have some kind of weaknesses. Which is a shame because we know that there is an extra information on nonlinear scales, and to really benchmark this and identify this, quantify this information, we organized a Beyond Two-Point Function Challenge with Elizabeth Krause, where we're testing the predictions of the EFT against different other models that typically are based on simulations. And in most of the cases, we're finding that the small scale simulation-based stuff would give you smaller error bars than the EFT. EFT was always given, the biggest error bars, which kind of makes sense because it's the most conservative approach. So this test suggested that there is some significant information on small scale, so it would be nice to take this information into account somehow. So yeah, we figure, well, omega matter, yeah, and sigma 8, you see that, for instance, this Baco will give you slightly better results on omega matter, right? But sigma 8 is really where all this SBI stuff shines and gives you much, much better results. Okay, even this like small volume kind of Quixote-based simulations, you see like omega matter is kind of very wide, but sigma 8 is basically, even this setup is better than like full volume the simulation. So we can beat the volume with these things naively. Okay. All right, so clearly both approaches, they have some weaknesses and merits. So okay, let's combine them. And the best way to combine EFT and simulations is to do so at the field level. And this is something that was subject of research that dates back to the time of approximate solvers like Cola and FastPM, etc. And recently now there are more discussions in terms of the tracers and so on and so forth. So basically, this is maybe the most optimal way to do the combination. So with my group, we decided to do the simplest possible combination. Okay, let's combine them at the level of the priors on the EFT parameters, because all the simulations, they represent UV models that give you some prediction for the bias parameters. Okay, let's measure all these bias parameters and use them as priors in the simulations, in the EFT analysis. So the problem is that in this case, we still need a lot of simulations to produce a big training set. And we can only produce a lot of simulations with small volume. Small volume means big errors. But then there is a, hopefully, well, likely there is a way to extract precision measurements of bias parameters from small box simulations by virtue of the EFT calculations at the field level, which really works like that we use the initial conditions from every simulation. We know the exact initial conditions, so we don't have to pay the price of cosmic variance. We can take the initial condition and model it, forward evolve it with the EFT equations instead of the full simulation. And here I'm showing you the results for the Millennium TNG simulation, which, the original simulation took maybe hundreds of thousands of CPU hours. And then you can compute the distribution of galaxies of particular kind using the EFT, and this computation takes less than a minute, and you can see that on large scales the distributions, they match kind of exactly. So clearly, on large scales the CFT field method seems to be working really well, and then we can measure all the bias parameters without having to pay the price of cosmic variance. So we have done that. We generated a lot of cheap simulations based on HUD, and then we obtained the following distribution and some subspace of the EFT parameters, and you can see that all the distributions are very non-Gaussian. So we use different ways to fit these distributions. So originally we used the normalizing flows, which is a nice tool from the machine learning toolkit, but recently we switched to the Gaussian mixture models, which is a way to both model these non-Gaussian distributions and analytically marginalize all these parameters in the likelihood. So for likelihood sampling, the Gaussian mixture models appear to be more efficient, but yeah, in principle, you can also use the normalizing flows. It's also fine. And then we apply these things. We apply these priors and actual analysis of the data from BOSS, which was the previous big survey. And we're able to find some really great improvements. So if you compare, for instance, here, the red blob against the gray blob, you see really big improvements, especially in the sigma 8 plane. And we were able to obtain some of the strongest constraints from galaxy clustering ever that were even stronger than the DESI year one results. And then the constraints that we got were as good as the constraints from the full SBI type methods. So this kind of suggested us that a lot of this power of the SBI that comes presumably from small scales is actually generated by having particular UV models, like more restrictive UV models than the EFT. So when you apply these priors on the EFT parameters on large scales, then you can extract almost all the cosmological information that otherwise you would get with the SBI. And then the advantage of this approach is that we can use this EFT-based, SBI as simulation-based priors. We can apply it to any data. So we can take the BOSS data, we can take DESI data with all of its volume. We can apply this, analyze this data, and then we're going to get better results than SBI because SBI only works on the small data sets. Yes, please. Yeah, yeah, that's right. Yeah, that's right. And marginalize over them. Yeah, yeah. We sample. We start from. We start with broad and informative big priors on HUD parameters. We sample. We generate these distributions and then marginalize over them. Yes. Yeah, this is an excellent question. So in principle, yes, you could do that. You can rerun it for every new physics model, but also we studied the cosmology depends on its parameters, and we found that there is a very strong degeneracy. So basically, all the cosmology dependence is degenerate with the halo mass. Okay, so for most of the applications, if you just sample your HUD parameters from wide enough priors, this effect of changing the halo mass will be bigger than any cosmology dependence. So that's right. Yeah, that's right. That's right. Okay. Yeah. Yeah. This is an excellent question. So how do we know this? Next slide. So we did the analysis with Stephen here of the BOS data without any HUD priors, just usual conservative priors, whatever. And when we included, we were super careful about the selection. And also we include some extra information in terms of CMB lensing and other things. And we're able to, again, get this low sigma 8 values, which, I mean, in the paper we suggest was going to be like this on systematics. And I think that also DESI, they confirmed the systematics because you can kind of, you can basically measure similar galaxies on the overlapping redshifts between BOS and DESI, and you will see the power spectra are different. So clearly there is some systematics going on. I think we just hit this systematics barrier. So in other words, this tension in sigma 8 is not a problem of simulation-based priors. And for instance, for DESI, there is absolutely no problem with this. We apply simulation-based priors, so don't find any tension whatsoever. Okay, so I think that this is a, we started with the error bars become very small. We started hitting some internal systematics in BOS. Are there any other questions here? Yeah. So we think that this is most likely imaging systematics because you can see that this signal is kind of generated on very large scales. Well, basically, if you assume, well, in general, if you have any kind of additive systematics, the systematics will exactly show up as a low value of sigma 8. It's just because it will, add up in the auto spectrum and cancel in the cross correlation. So when you compute the usual kind of RSD constraints, you always compare like you do the quadrupole to monopole ratio, monopole will always appear bigger, right? So any systematics will give you a low sigma 8, and the systematics that we kind of suspect is most likely is imaging systematics. The what? Well, here we did different tests on the covariance in the end. We think that, we did analytic covariance, we did the covariance from the MOX. It was not making a big difference. So I think that for covariance, we know that most likely it's not because of that. Any other questions? Okay. Yeah, something that we also tried is like, okay, there is some problem with sigma 8, whatever, let me just close my eyes and let me analyze DESI data with BOS. And then even in that case, we're able to see that if you add BOS full shape, in addition to, DESI, so you can see this, there is a beautiful 3 sigma DESI result, you add the full shape even without any simulation-based priors, you already start being consistent with the cosmological constant, and then the consistency kind of increases as you add the simulation-based priors. So already back in the day, it was kind of clear that these tools will play some role in the dark energy constraints. But however, again, you might be kind of skeptical about all the simulation-based prior stuff. So to validate the simulation-based priors, we also did some precision tests against full numerical simulations, MTNG and Astrid. So the idea was that we just took the data from the simulations and we selected the galaxies that match the most precise way the actual observed samples in terms, well, in particular, well, here you can see the distribution of these galaxies from simulations, from Millennium and from Astrid. The distribution is slightly different, which kind of underlines this dependence on the subgrid physics model. And then, so in this plot, I'm showing you the stellar mass and the specific star formation rate, parameters from simulations. So there was a nice paper by Bariana, Hajriska that showed that the cuts in the specific star formation rate, they correspond to the cuts in the color that, then will match the actual colors of the observed galaxies. So basically, we optimized this cut. We generated some relative luminous galaxies, emission-like galaxies. Then we measured their parameters at the field level, and we obtain the following distribution. So here you can see that there is a gray band that is produced by these HUD priors, and then different points that correspond to different galaxies, well, sub-selections from the Hydra seams, and you can see that overall we're able to get very good consistency, even though even if you want to use the same cuts, in different simulations, you'll get slightly different bias parameters. But then all the correlations between them, all the trends that we obtained with HUD, they also were followed by the Hydra galaxies. So that kind of suggests that probably we can trust the simulations at the field level. Maybe one thing that you can notice is that the agreement is not as good for the blue galaxies that correspond to the emission-like galaxies. And this is because we're comparing them against the HOD forms specifically fit to the LRG galaxy. So they have emission line galaxies, they have different HODs. So the HOD now is not a Heaviside step function, it's more like a Gaussian. So now we're generated additional subsamples of these HOD priors, specifically from this kind of HOD parameterizations. And then after that, the distribution of emission line galaxies from the HODs were following the distribution of emission line galaxies for hydra seams very, very closely. So we got, again, a perfect agreement in terms of the trends and correlations. So that suggested to us that what we're doing is not so bad. Okay, maybe last point that I would like to make, following the earlier question on the cosmology dependence, is that actually we can also develop some basic analytic understanding of the EFT parameters. And in the context of some semi-analytic models, just like the Halo model, we can calculate that the bias parameters of galaxies of particular type is basically are given by the bias parameters of halos weighted with the Halo mass function and with the HOD form, with the HOD distributions. And for Halo bias, we know this dependencies really well from numerical simulations. You know, all the results, they converge really well. So we know this function super well. And the HOD is something that we come up with ourselves, right? We come up with this parameterization. So we know this function. In other words, we can evaluate this integral analytically, and then you can generate this prior distribution analytically, like in no time, in a few seconds. And then you can see that it will match with, let's say, 10% accuracy, the result of actual full, kind of blown simulation. So that's a cheap way maybe to go beyond lambda CDM, because so beyond lambda CDM, what you will need to know, well, basically this kind of dependencies, even in BSM models, they kind of hold, so they don't change, and the only thing that will change will be the Halo mass function. So that's like a cheap way to check that, BSM models, to generate priors for BSM models. Well, there is this notion of universality that, well, basically you can understand that the Halo bias can, there are some arguments like from the peak background split that it comes from, there's a pressure picture, you have halos, and then you have a little assist from a long mode. And as a result of this picture, you will see that well, you can compute these things, and you will see that they will depend only on the stuff that is going on in the Halo mass function. And the Halo mass function is universal. That means that it depends not on the mass, but always depends on this pressure parameter nu, which is the critical density divided, well, squared, let's say, divided by the mass fluctuation filtered at the scale of the halo, right? So all your cosmology dependence and stuff will be just captured by this. Right? Yeah, and yeah, people have checked this. It has an extremely weak response to any BSM model. We can include this in principle, but then delta C changes by like 0.1%, right? So, I mean, we can include this. You can compute, in your BSM model, we can compute what delta C is, but in principle, the effect is completely negligible because it's all going to be absorbed by this HOD, which is like 100% uncertain, basically, right? Okay. Yes. Yeah. Absolutely, yeah, that's a really great point. I think that the simplest way to do it is to just increase the variance of these parameters, the spread of these parameters that you can do by hand. So one way to do it, for instance, you can design this Gaussian approximation to the full HUD, and then you can just increase the variance by whichever factor you want, right? That's one way to do it. Yeah, yeah. This is a beautiful question. I feel like one of the ideas that I had after looking at these things is that what we're doing with EFT somehow is is wrong because we write down so many parameters, right? And that happen to be extremely degenerate from the point of view of HOD, right? So maybe there should be a way like to diagonalize this in a HOD kind of friendly or hello friendly way. That's right. Yeah, that's right. Like for instance, what you can see, one of these parameters, the tidal bias, cubic, p gamma 3, is always like a super tight function of BG2. So it's basically exactly the same thing. So I think that, yeah, we should just, I mean, the simplest way is just to read these kind of dependencies and try to, you know, reparameterize our EFT precisely to match these correlations. This would be one way to do it. Matt, yeah. Mhm. Right. Yeah, one way to study this maybe in the context of EFT would be like to really understand the RG flow. It could be that like what we see here is just the result of the RG flow, right? That's one way to kind of make a better connection with the EFT. Yeah, 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 sure. I mean, you take one of these codes and then you just, you know, compute the power spectrum mostly. Well, unless your model changes the kernels and then, okay, good luck. You have to really modify then these things. But as long as your model only, if your model only modifies the initial conditions, sorry, I'm just going back all the way. If it only modifies the initial conditions or the expansion rate, then you can use like any of these codes out of the box, basically, right? Now, if you have additional clustering species that will modify the nonlinear kernels, then I would say you'd need to like really code them up. And you know, we had this discussion that it would be nice to optimize these things to make it more friendly to BSM modelists. But at the moment, I think that's the most robust way to do, right? Just do the full forward model where you calculate all the kernels and all the shapes and yeah. All right. No, yeah. Right. So I mean, we tested on some of these SBI methods, like the wavelet scattering transforms, and very roughly we're getting basically the same results from the HUD prior. So actually, in this SBI techniques, like a lot of improvement comes by like having fixed HUD model, right? And like a lot of these SBI techniques, for instance, they use the, the so-called vanilla jank model that only has 6 parameters. Now this model is super constraining, right? Like you can get a lot of, if you apply these priors in the EFT context, you're going to get like sigma 8 like to 1% from boss, basically, right? That also be like 10 sigma away. So yeah. But yeah, we try to kind of quantify these things, and it seems really that basically all the information that is there in the SBI you can capture, or like the bulk of it you can capture by just applying the HUD priors. Like in other words, this what small scales give you is really the bias parameters, right? Okay, here. Oh yeah, yeah, excellent. Yeah, excellent. Yeah, yeah, we account for that. Basically, you can compute like the RG scaling, so you can compute the UV limits of all these what to call transfer functions, and you can match, you can account for the mismatch between having a finite cutoff because of the pixelation, and you can run away. And the answer, at least one loop order, actually is if you just fit um, you take whatever output of transfer function and you just fit it with zero predictions, evaluate it at the infinite cutoff. This will already give you the same result as the running, right? Which you can prove at the one loop order is the exact result. It's the same way as when we match like, sound speed, for instance, right? You want to measure the sound speed, let's say from simulations. We always assume lambda is infinity, right? We measure some value like 1 or something. We don't need to account in principle. You can account for the running. But now if you consistently use the same kind of randomization prescription, all the measurements, you're going to get the result in this randomization prescription. So at one loop order here, you can do this. You can check this. That, well, basically, if you, yeah, it's very easy to account for the RG running. Okay. Yeah. It also, we measure all the stochasticity parameters as well. I mean, at the moment we measured only, yeah, like this alpha, not alpha 1 is like the constant stochasticity related to the exclusion effects, and alpha 1 is the like the k-square term. Yeah. I mean, it would be nice also to measure like the stochasticity of this from the bispectrum. So that is also, okay. Here we're only measuring the power spectrum parameters mostly. Okay. All right, are there any other questions? Yes. Yeah. Yeah, that's really a tricky question. So what ideally we would like to do is we start with extremely broad and informative priors, which we try to do in all these cases. Now what happened because of BOSS, it has this like sigma 8, whatever little tension. What happened is that the actual kind of EFT best fit happened to be sitting like in the tail of the distribution, right? So we were thinking, okay, maybe we would need to like rerun these things, but also it seems like a wrong from the Bayesian point of view. So what we do at the moment, we define a very broad range, hoping that it will work out, and then at least for DESI, it all worked out. But for BOSS, there was a little bit of problem because of that. Yeah. Ideally, I would say you need to really, sample the broadest possible thing. Oh, oh, okay. Oh, yeah, yeah. Oh, yeah, 100%, yeah. That's right, yeah. Probably like updating the distribution. Yeah, probably. Yeah. I mean, I was worried a little bit about these conceptual things, like as a Bayesian person, can you update your prior based on the data? But yeah, in principle, like from a practical perspective, this makes sense. Yeah. Right. Right. I mean, that being said, again, as Marcus said, we really have very broad distribution. So for instance, for BOSS, I find B2 to be here, like 2. Okay, so you can see that it's kind of a tail of distribution, but you still have like thousands of samples here. So you still have enough, uh, enough samples to generate an accurate distribution. All right. Any? Yes. Yeah, we feel it really okay. We feel it really at the level of the fields. So you say that you have delta truth, right? Which is your delta simulation minus delta model, and then we try to minimize this in every k bin, right? And then you can prove that this is equivalent to computing certain correlation functions. So for instance, for B1, this is just, well, basically delta matter, delta galaxy divided by delta matter, and cosmic variance cancels, right? Because if you have fluctuations here, you also have the same fluctuation here, right? So this is very roughly. So we minimize this, but then this is equivalent to computing the bias parameter. Like this gives you values, the optimum values of the bias parameters that basically will look like that, right? Yeah. Yeah, every k bin. Yeah, exactly. So yeah, well, every single point is a specific like B1, right? Specific simulation. And then we come up with this normalizing flow or Gaussian mixture model is just a fitting function for the distribution itself. Already this distribution. So we obtain just like a set of things, B1 like 1,000 values, B2 1,000 values. So this distribution, and then we fit with this tools. So normalizing flows, you just feed in the samples, it will produce you the function that will then tell you what's the likelihood, okay, for a given point. Well, the Gaussian mixture model is kind of the same thing. It generates, it tells you what are the optimal parameters, you see how many Gaussians you want to keep. It just generates you the distribution of all the parameters. And again, you can calculate for every single set, like B1 equals to, B2 is 0. What's the likelihood, right? Yeah, sure. Yeah, every single HUD model gives you like an exact prediction of what B1 is. There is no stochasticity. Yeah, exactly. Like HUD model with this HUD parameters will give you the exact value of B2 1.6. Exactly. We sample a lot of HUD parameters. For every single one of them, we compute these things. This is the distribution that we get. Okay. Any more questions? Okay. Um, very good. All right. So we discussed these things. Okay, just very briefly, something about the one loop bispectrum. So there's been a lot of work, a lot of activity, different groups working on the one loop bispectrum. And I think that now we have converged more or less to how this one loop bispectrum should look like. Now, kind of the biggest practical problem with the implementation of the one loop bispectrum was that it's slow. So typically when we compute the predictions for a given linear power spectrum, we expand this linear power spectrum over some basis of functions V, which are analytical functions for which the one loop EFT integrals can be computed really analytically. Like in FFT log, this will be just some polynomials. Now for the one loop bispectrum, the loop diagrams will generate terms that involve three like integrals over the three insertions of the linear power spectrum. Now you can kind of plug in this expression here and do some math. And then you will see that your calculation will reduce to some matrix multiplication of a relatively big matrix, because the problem is that if you want to fit the shape of the linear matter power spectrum with some simple functions such as polynomials, for high precision, like 0.1% precision, you will need to keep track of a lot of elements, like 100 elements or so. So very quickly, this becomes a gigantic matrix, and the whole thing becomes very slow. Now, there is a nice approach by Thomas Bach and Zvonimir Vlach to use the singular value decomposition of some template bank generated for different cosmologies to identify kind of the basis in the latent space of the different linear power spectra. And then in this case, you can basically come up with numerical functions V for which you can capture the cosmology dependence to 0.1% precision. And then turns out that for, let's say, DESI precision, it's enough only to keep track of 4 principal components. So if you only have to keep track of 4 basis elements, then this matrix becomes very small, and you can calculate the one loop predictions in less than 1 second. And then we check this against the full kind of numerical calculation, and we were able to obtain for observationally relevant case of the bispectral monopole, the precision was like below 10 to minus 4. So this method works extremely well. And this allows you to get the fast and accurate one loop bispectrum analysis. So now, having presented all these tools, let me finally discuss the DESI results. So for DESI, we use the public data on the full shape of the galaxy clustering from the data release 1. We have created our own completely independent custom likelihood based on our own kind of estimators, window free. So we can undo the survey window functions. We have the streamlined treatment for the survey systematics. So Oliver has a new ingenious way to account for fiber collisions in the bispectrum for the first time. We apply these things. We measure different clustering statistics. We measure the bispectrum from DESI. And in the 4 out of 6 DESI samples, we're able to detect the bispectrum on large scales very significantly. You see that the problem with DESI year 1 is that there is significant shot noise, like the mission-like galaxy sample and the quasar sample are shot noise dominated. But for the rest of the galaxies, we detected the bispectrum. And now we can kind of feed all these things consistently. And these are the first results that we got by just feeding the Lambda CDM. So here the big blobs are the results from the power spectrum and then bispectrum and the BO from DESI versus the CMB. And you can see that in general, when you add the bispectrum, the contours, they move slightly towards the Planck Lambda CDM values. So the full shape of DESI year 1 happened to be in a little bit of a tension with Planck, but this tension can be reduced by including the bispectrum data. Oh, this means that we add the BO, the post-reconstructed BO from, in that case, from DR2. So DR2 has, for DR1, it will be hard because of the cross covariance, but DR2 has such a big footprint. So like the overlap is tiny, so we can clean order, just ignore it, and then we can account for it. Right, so this means BO from DR2 and full shape from DR1. Okay, something that is close to my heart is the measurements of the galaxy bias parameters from all these different samples. So here you can see, well, the different distributions of quadratic bias parameters as a function of linear bias. You can see the predictions, well, the measurements from the halos, and really it's like a delta function. So that's why we wouldn't need AFT if we could measure halos. But however, for galaxies, there is some scatter produced by the HUD sampling, and each point corresponds again to a different HUD model. And you see that as a result of this HUD weighting, the bias parameters of galaxies in general are different from the bias parameters of halos. And in principle, okay, it's a detectable effect. For B2, our error bars are too big yet to kind of rule out the B2 of halos. But for instance, for the tidal bias, our measurements kind of already at the 2 sigma level kind of already tell you show some departures from the halo-based predictions, which I was thinking is a nice consistency check. Well, DR2 has a big footprint, and DR1 has a much smaller footprint, right? Right, but DR2 will be dominated by the rest of the survey, right? Yeah, it's a bigger sample. It's like basically you have this kind of situation. So this is DR2, and this is like DR1 roughly, right? So DR2 is dominated by this. I mean, even in that case, your DR2 will be dominated by this, right? This is true, but since this is so big, this will be, your BEO basically is always dominated by this, and whatever it does is like an epsilonic correction. You're double counting an epsilon, but still an epsilon, right? So that's why you can ignore. I mean, then we can include this covariance. We can compute theoretically. Yeah. It's like, I don't know, around 20%. It's, you know, we can take a look at these footprints, but like it's, yeah, something like this, 20, 30%. But again, in principle, we can include the cross covariance, right? We can do analytical calculation. With, you know, it's a small effect. At least in order you can ignore it. Yes. Um, the, surprisingly, the coevolution seems okay, but this is like an artifact because you see for the halos, the coevolution is kind of ruled out, right? But then you have this HOD weighting that pulls the galaxies a little bit kind of below, and they happen to match the coevolution in this particular range of B1s. But if you go to like higher Bs, you see that there is a difference between them, right? So for galaxy, yeah, it works. I mean, it's an accidental thing, but yeah, the coevolution is okay. Okay. Any more questions? All right. Okay, finally, the undetection of dark energy. So the first thing you can do is just do CMB plus BO plus all this extra stuff. And then you can see, even if you just add the power spectrum, then already your contour moves from 3 sigma to less than 2 sigma. And then you add the bispectrum and the contour becomes a little smaller, but still consistent with the cosmological constant. And then the simulation-based priors kind of will push your measurements even closer, towards the cosmological constant. So this is the first observation. This is without supernova, very crucially, yes. Now, with the supernova, yeah, this is a little puzzling, but I can tell you the following, that these contours are like fully converged. So it's not a convergence issue of MCMC. So really, I feel like there are certain degeneracy directions that maybe for what we call the conservative priors, maybe are not so conservative actually in some dimensions. This is my, yeah, yeah. I feel like order one priors might be too aggressive in certain directions. This is my interpretation. Any more questions on this one? Okay, no supernova, important caveat. Now, with the supernova, it's really hard to beat them, right? Because supernova plus the BODR2 really wants to pull everything towards Wawa. So for instance, if you just do the usual kind of data set, power spectrum, bispectrum, supernova, you're still going to have like a 2.5 sigma Wawa detection. But with simulation-based priors, it really, they really push you back to the lambda CDM. Well, there is still a little bit of like, 2 sigma-ish something, 2.1, but the evidence is reduced. So this suggests, again, if you believe in all these tools, that the W1WA is simply a statistical fluctuation, so no new physics is required. Yeah. Oh yeah. Oh, is more consistent. Yeah, this is exactly kind of the point why it's helping, because omega mater, you can see in this plot, is moving with the bispectrum and stuff, is moving towards the Planck. I mean, again, we're talking, it's not a big move, but we're always talking about like 1 sigma statements, right? Because here, yes, that's right. Um, this, well, because well, you need to think multidimensionally about these things. Yeah, yeah. So yeah, it's in a cocktail. Well, you see that like with this combination, you have extra degeneracy direction. So now if you add, well, there is still a little bit of like tension or something, but there is less tension that you would have with just BEO. Yeah. No, no, only for the BEO, because you see omega mater, the shape gives you a totally independent like prior on omega mater, just like supernovae. It's quite good. It's relatively well measured. Omega mater is, well, it's enough like to move these things by 1 sigma, right? So I think it is comparable. Yeah, actually, we check these things like with omega matter from all of the, the constraints were similar from the shape and from the BEO. So it gives you an additional kind of independent measurement of omega matter in this cocktail. Okay. Now, finally, okay, these results were presented for the tree-level bispectrum. Now, what if we add everything, everything, everything? So these are the preliminary results. There is still, chains are still running and converging. Here we have the full blown one loop bispectrum multiples, and also we've added some cross correlation between the DESI galaxies and the CMB lensing. And you can see that this kind of story that in general, the WAWA detection is reduced, is still there. Now the exact kind of statement about what is the tension with cosmological constant, this changes a little bit, from 2 sigma to 2.2 sigma or something. But you can see in general that this full shape stuff produces much more narrow contour, and this contour is more consistent with the cosmological constant. This supernova is the Pantheon Plus. Yeah, obviously, if you start adding other supernovae that are less consistent with lambda CDM, you'll have a little bit of more kind of discrepancy, but the story will be the same, that the full shape will put, as much as it can, like 1 sigma, it will be reducing by 1 sigma all these preferences. So here, the K-max is 0.16, but we also check that, for instance, if you just close your eyes and do K-max 0.2, still, the results will be similar. And this is because the one loop bispectrum is of DESI 1, year 1 is short noise dominated, basically. In these plots that I showed you before, you can see that kind of short noise kicks in really quickly. So that's why the short noise, well, because of that, for instance, here for LRG2, I mean, quasars and LRGs. So that's why you don't gain as much, but you still gain like, 30% omega matter constraints. Sorry, this is this was the K max for the bispectrum. Yeah, so I mean, we like yeah. Well, I think that the statement is the following, that the so in terms of cosmology, like H naught and omega matter, you can get extra information through various things, through the shape and also through the Alka-Paczynski effect. But for instance, for sigma 8, we didn't find any improvement. And the only improvement that we get comes from the bispectrum quadrupole. And this improvement is like maybe 20% or something. But like, for instance, monopole doesn't improve sigma 8 constraints at all. And in terms of H naught and omega matter, we understand very well where this information comes from, again, from the shape and from the Alka-Paczynski. Okay. Yes. Okay. I mean, this was basically it. Okay. This is the summary. I hope I've convinced you that this EFT full shape is not useless, that it gives some competitive constraints on the WNWA, so it can make a difference for BSM models. We have results that suggest that the DESI WNWA is a statistical fluctuation at the moment, but again, it's like a 2 sigma statement. And we expect more improvements in the future with DESI DR2. And like key to making these improvements and making these tools more robust is really studying better this non-perturbative information, how to interface information from simulations and EFT to boost the constraining power. So with that, I'll stop. Thank you very much. No, here there are no HUD priors. I have a plot with HUD priors that I can. All you see is like factor. Oh, you mean like a yellow against the HUD priors? Oh, the B alone. Oh, the B alone is it's slightly larger, but I don't know the exact number. Yeah, we can. Well, actually, I might have some backup slides. Yeah. Okay. Maybe. Oh no, this is full shape and full shape plus B. So Okay, we can look these things up.